Today we're going to learn the relationships of current, voltage, and resistance in both series and parallel circuits. We're going to start off by looking at series circuits. And there are three equations that govern these quantities in series circuits. So let's take a look at current in a series circuit first. We know that in a series circuit, the current is the same. So if you know the current past one point in a series circuit, you know the current past all of the points in a series circuit. So we write this with the equation total current is equal to current 1 is equal to current 2 is equal to current 3 is equal to however many loads you have in the circuit. For voltage, the total voltage is equal to the sum of the individual voltages. So if you know the individual voltages, you can add them up to find the total. For resistance, it's similar to voltage. So if you know the individual resistances, you can find the total resistance. So we're going to do three examples, one for each of these equations. Whenever you're doing these equations, I suggest that you write down the equations right away on your page. So you have them there so you can look at them while you're answering the question. So let's take a look at the first example. Example number 1. Calculate the current of each component in the circuit. So I've written my equations for series circuit right on my page, and I've been given only one of the currents. Looking over at my equations, I know that the total current is equal to current 1 is equal to current 2 is equal to current 3. So all of these must be 0.30 amps because they are constant. Let's take a look at example 2. In example 2, we're investigating the voltage at each point in the current or in the series circuit. So we're given the voltage of light bulb 1, the voltage of light bulb 2, and the voltage of light bulb 3. Our job is to find the total voltage. So we look at our equations, and the equation for total voltage states that total voltage is equal to V1 plus V2 plus V3. So we can add these individual voltages together, 1.5 volts plus 2.0 volts plus 2.5 volts. If you punch these into your calculator, total voltage is equal to 6 volts. The third example has us looking at resistance. And the equation for resistance in a series circuit states that resistance 1 plus resistance 2 plus resistance 3 equals the total resistance. This time, they've given us the total resistance. They've given us 9 ohms as the total resistance. They've given us R1, it's 2 ohms. R2 is 4 ohms. But they don't give us R3. Now we can look at this expression and say that if the total is 9, and the individuals are 2 and 4, what remains is 3. 2 and 4 is 6, plus 3 would give us 9. So you may be able to look at that and find the answer right off the bat. But if you don't see that easily, then we're going to use mathematics to solve this equation. If we want to isolate for R3, we have to take these variables and bring them over the equal sign. When we do bring variables over the equal sign, their sign changes. So these will go from being positive to being negative. So once we bring them over, we write the expression as R3 is equal to 9 ohms minus 2 ohms minus 4 ohms. If you simplify this in your calculator, you will see that you get an answer of 3 ohms. There are 3 equations for parallel circuits. For parallel circuits, voltage is the same across every component. So if you know the voltage across one component, you know the voltage across any component. For current, the individual currents add up to the total current. So these are the 2 equations for voltage and current for a parallel circuit. If you compare them to the equations for a series circuit, you'll notice that they're opposite. In a series circuit, current was constant and voltage was equal to the sum. But now for parallel circuits, voltage is constant and current is equal to the sum. Now total resistance is a little trickier for parallel circuits. It's got this fancy equation, and the fancy equation is written like this. 1 over the total resistance is equal to 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3. So we're going to take a look at an example, or 3 examples using each of these equations. Whenever you're doing these examples, make sure you write down these equations straight away. In example number 1, we have 3 light bulbs and they're connected in parallel. And we want to determine the voltage at each of the components. Now in this question, they only give us one voltage, and that's the voltage of light bulb 3. But it won't be a problem to solve this because the equation for voltage in a parallel circuit says that the voltage is the same. So total voltage equals V1 equals V2 equals V3. So if you know any voltage, you know them all. So we can say Vt must be 4.5 volts, V1 must be 4.5 volts, V2 must be 4.5 volts, and we knew that V3 is 4.5 volts. So they're all 4.5 volts. In example 2, we have 2 light bulbs connected in parallel. We know the current past light bulb 1 is 0.3 amps, and the current past light bulb 2 is 0.2 amps. If we look at the equation for current in a parallel circuit, we know that total current is equal to the sum of current 1 and current 2. So we can sub and solve and say total current is equal to 0.30 amps plus 0.20 amps, and the total current is 0.50 amps. In example 3, this is the most difficult. It's finding resistance in a parallel circuit. So we're given 2 individual resistances and we want to solve the total resistance. The equation that we're given for parallel circuit says that 1 over total resistance is equal to 1 over R1 plus 1 over R2. So if we sub in what we know that 1 over total resistance is equal to 1 over 2 ohms plus 1 over 3 ohms. So now we're set up with fractions, and we have to add fractions. So this will take us back to elementary school where we added fractions. We have 1 over 2 and 1 over 3. You notice that these fractions have different denominators. In order to add fractions, you have to make sure they have the same denominator. So we look at the denominators, 2 and 3, and we try to find a common denominator, a number that is common to both. So we can determine that 6 ohms would be the common denominator. So we'll try to solve this. 1 over RT is equal to, and we put in our common denominator, 6 ohms. So let's review how to add fractions. Well, the first fraction had a denominator of 2. What do we multiply 2 by to get 6? 3. So we'll multiply the numerator by 3. Next, the second denominator is 3. what do we multiply 3 by to get 6? 2. So we'll multiply this numerator by 2. If we simplify this expression, we're left with 1 over RT is equal to 3 plus 2 over 6 ohms. So now we can add the numerator. We have 1 over RT is equal to 5 over 6 ohms. And it looks like we're done. It looks like we found the answer. But remember, what we wanted to find was RT. And what this has given us is 1 over RT. So if we want to find RT, it would be helpful if we could flip this upside down. So if we flipped 1 over RT, it would be what we want. So we can flip both sides. And we're left with RT over 1 is equal to 6 ohms over 5. Punch this into your calculator. 6.0 divided by 5. And the answer is 1.2 ohms.